This is the lower layers track, and you are here for Windows 8 heap intervals with Chris Valasek and Tarjei Mandt.
All right. As the flyer read, this is Windows 8 heap intervals. I'm Chris Valasek. I'm a senior security research scientist at Coverity, and this is Tarjei Mandt. He's a vulnerability researcher at Azimuth Security. We do a lot of heap research, if you haven't noticed. So what are we going to cover today? We're going to try to look at data structures and algorithms in the Windows 8 release preview. That being said, this may change when, October 26th, whenever the actual product is dropped. But I think it should give you a pretty solid overview of what's going to happen. After we go over some data structures and algorithms, we're going to talk about all the security mechanisms put in place, and there are definitely plenty of them. And finally, I hope that we can go over some exploitation techniques that Tarjei and I have came up with that are applicable to Windows 8. While not as plentiful as in years past, they still do kind of exist. So if you haven't already read the two papers that Tarjei and I wrote before, you might want to read those as prerequisite material before you kind of get into the Windows 8 paper that we released with this presentation. Also, there's a bunch of other people who do a bunch of good heap work. Obviously, check that stuff out. Why do you even want to learn about this? It's 2012. Why is heap stuff even important anymore? If you're going to do anything with heap-based memory corruption vulnerabilities, you can't really just play guesswork and hope to win. You need to understand the underlying operating system and application and how they actually manage their memory and what you can do to leverage certain pieces to achieve your goals and gain more exploitation primitives. That being said, if you have heap exploits that work in Windows 7, most likely they are not going to work in Windows 8. I'm sorry to burst everyone's bubble. Feel free to leave now if you don't care to learn why that happened. But that being said, let's try to move on here and see what actually we're going to cover. First, I'm going to talk about the user-land backend heap. This is probably the most familiar to people. It's the doubly linked list structure that everyone's kind of used to since seeing it, a long time ago. We're also going to cover some mitigations in the backend. It is strikingly similar to Windows 7, but not exactly the same. So I know this is probably hard for some of you to see, but in Windows 7, I created a diagram that is very similar to what I'm showing you right now. Before, though, there was this backlink in the list hints, and that backlink kind of serves the dual purpose. It contained a counter to lazily activate the low fragmentation heap for certain sizes, and occasionally it would contain the address of a heap bucket data structure, which would then be passed to the front-end allocator and used for allocation. This has now changed. They no longer use this backlink. There's actually been another data structure added to the heap base structure that is specifically used for counting and indices into the heap buckets. It's called the front-end heap usage data structure. And also as an optimization, instead of checking this backlink, they now have a bitmap where they can say, hey, at this index within the bitmap, is it a 1? If it is, we're using the low fragmentation heap for this given size. Those are some things that have changed. While not drastic changes, they're changes nonetheless. On to the kind of exploitation mitigations. And like I said, there's a lot of these. The first one I'm going to talk about is back in 2008, Ben Hawks, if you're counting name drops, that's going to be one. It may happen several times. Ben Hawks came up with a technique where if you could free a heap handle and then subsequently allocate that memory, you could overwrite the heap handle with data that would permit the attacker to get code execution upon allocation. This was actually prevented in the Windows 8 backend manager by checking the chunk that you're freeing. When you free it, if it's the same heap that's freeing it, it's going to report failure. Therefore, if you're trying to free a heap handle as the chunk to be freed, it's not going to work. There may be a corner case where you could potentially get a heap to free a different heap handle, but I would just say that's probably not going to happen. The more complex of these is what they did with virtual allocated memory. Before, there was a possibility that you could have predictable virtually allocated memory. That is, you could have one big chunk on top of another big chunk, and if you had an overflow, you kind of had a very good idea of what would be where. This has changed in Windows 8, and changed quite drastically. Again, the code is kind of small, but what they do now is if the size that you're requesting should be serviced by the virtual memory allocator, it's actually going to create a random offset, and it's also going to add some extra size to the actual amount of memory that's needed. And what this achieves is two things. The offset for this virtual header is not going to be predictable. You won't know exactly where it's going to be in this overall chunk. And also, since they reserve the memory and then only commit a different amount, each of these virtual chunks, these large pieces of memory, are going to have reserved memory above it, in hopes that if there is a sequential overflow, it hits this reserved memory and an access violation occurs, therefore rendering your overflow useless. So that didn't seem too bad, right? There weren't too many changes. It worked, fairly well. There's just some exploitation mitigations. Now we're going to talk about the user-land front end, or the low fragmentation heap. There was a lot of changes to algorithms and data structures in the front end. RTLP low frag heap alloc from context is the main allocation function for the low fragmentation heap. And when bin diffing it with the preview versions and Windows 7, they didn't actually come up as matched functions. So that's how much the functionality and data structure access changed in those things. That made it very not fun to start analyzing. We talked about the mitigations in the back end, and now we'll talk about them in the front end as well. We first saw how the front end activation heuristics are triggered, right? No longer is that backlink used for everything. There's dedicated data structures and a bitmap to do it. We're going to go over in a bit of detail how front-end allocation actually occurs now. There's no more free entry offset if you're familiar with the free entry offset overwrite technique. It's been removed. Also, allocations are less deterministic than they have been before. We'll go over that stuff and then continue with the mitigations listed below as fast fail, and there's the guard pages and more anti-exploitation technology. But before we do that, let's revisit Windows 7 real quickly. The Windows 7 low fragmentation heap used this heap user data header, which preceded a thing that I refer to as the UserBlocks. Basically, a user block container contained chunks of memory, and each chunk, the first 2 bytes, was it was the free entry offset, which pointed to another free chunk in this overall container. The allocator blindly trusted this value and used it in its calculations. So here's how allocations would go in Windows 7. Say you had this virgin user block container where no chunks were busy, and you made an allocation. You see that the free entry offset is updated with the value that was there, and the depth is decremented. You make another allocation. It comes from the slot next to it. The free entry offset is updated, and so on. So you see that it basically trusts this value and use it to provide free chunks to the calling function. Windows 8's changed quite drastically in this fashion. You can see the heap user data header has many more members. One of them that caught my eye as soon as I saw it was guard page present, which is foretelling about what you'll see here shortly. Other neat things to notice is there's a first allocation offset. And this is basically was implied before because it was always after the heap user data header, but now it's a set value. And also there's a member called the BlockSize that basically just says how big are chunks that I'm managing, how big are they. You'll see that there's no more free entry offset in the user block chunks anymore. It's just not used. Instead, they use this bitmap. And each index in the bitmap represents an offset into the UserBlocks container. And there's a 1-to-1 ratio of how many chunks there are on the user block to this bitmap here. I talked about randomness and non-determinism before. How exactly to do that? It wouldn't be manageable to generate a random number every time you make an allocation. The overhead would be too great, right? So instead, they created this array and actually populated this array with unsigned 8-bit integers. And these unsigned 8-bit integers are used as offsets into this bitmap, which will then be used to service a request and get a chunk from the LFH. So if you're wondering how that occurred, it's not a random integer every time an allocation is made. It's actually pre-populated and updated occasionally as well. So just like the Windows 7 allocation, let's assume that we control all the allocations, and this is a virgin user block with no busy chunks. The first allocation won't actually be from that first slot anymore. It's going to be at a random value. So we'll say the bitmap was chosen, and it looked at offset 5. And it said, yes, that's a free chunk there. You can give the offset 5 back. We're not actually going to get offset 6 as the next one if we make a subsequent allocation. It's going to be another offset within this bitmap. You may be asking, what happens when the bitmap actually misses and it actually selects a busy chunk? It will actually then start sequentially looking for free chunks. So if you guess offset 5 and you want to, and it's busy, it's going to go look at offset 6, 7, 8, etc., looking for chunks that are free. So this kind of hinders the process of knowing exactly where your chunk is going to be in relation to data that you want to overwrite. It also could really mess up kind of use after free bugs as well. You can't just alloc free alloc again. You're not guaranteed to get the same memory at the same address back. So like I said, Windows 7, kind of sequential, if I may, allocations. There's a free entry offset you can overwrite. Pretty straightforward. Windows 8, you have this randomized, non-deterministic way of allocating memory. There's no free entry offset, so chalk another one up for exploitation techniques dying in Windows 8. But let's talk more about what they did as well. There's a thing called fast fail, and I think the first person really to publicly mention this was Alex Ionescu on his blog. It's basically a way, an interrupt to terminate the process immediately. And they're actually used when checking linked lists to ensure that they're not corrupted. There's times where if the terminate on corruption flag isn't passed to heap set information, the API, it will log a report, but it may not terminate the application. As a developer of Windows code, you may not want to rely on people doing things properly. You may want to just terminate the process right there, and this is exactly what it does. You'll see here that if the doubly linked list is considered corrupted, instead of calling a logging function and seeing if the right flags are set, it calls int29, and the process will be stopped. You should go look at this function in Windows 7. Guard pages, as we talked about before, with the guard page present flag. I think this might affect sequential heap-based buffer overflows the most, maybe in comparison with the random allocations. The heap user data header now, instead of just allocating a big chunk of memory and chunking it out and potentially storing other user block containers adjacent in memory, will tend to look at things first. It will actually say, hey, how many chunks of this certain size do we have? If it's above 1024, next time this time around when we're creating a new user block container, add a page to it and make that a guard page afterwards. Also, if the size is really big that you're asking for, which could be used in a spray, it also will say set the guard page appropriately. Like I said, before you had this function that would allocate memory, chunk it out, and that'd be done. Now, when RTLP allocate user block used to just allocate the memory and be done, it actually calls RTLP allocate user block from heap. And you can see in this code right here, it allocates the memory. And if it says the guard page should be set, it's going to add a page size and then reallocate the memory, and then set that page at the end to page no access. Effectively, what this does, if you try to read or write to those addresses that are set as page no access, Access violation, you don't win. And again, this could greatly affect heap spraying, sequential overflows, things like that. It definitely will make things much harder. And here's just a brief example of theoretically what could happen with these guard pages. Before, you would have user blocks for the heap bucket 6 and 8 and 6 all kind of together, contiguous in memory. Now they're going to actually be separated by these guard pages, so an overflow from one user block container into another will cause an access violation if the heuristic is triggered. Again, they really paid attention to Ben Hawks's research from 2008. He also came up with a way to, with an overflow, overwrite some information in a heap's chunk header. The way, if there were certain flags set, the header would actually be relocated to a new position. And if you could trick it into relocating to a position within the low fragmentation heap, you could actually free memory that wasn't supposed to be free and was busy and create a use after free condition. Now, when they do the initial header relocation, you see here that if it's set to a certain value, it's going to subtract from its current position to get a new header. But now, if it's in the low fragmentation heap, it's actually going to call RTOP validate LFH block. And that's going to guarantee, hey, if this is the type of chunk that gets relocated, is it really that type, or is this attempted exploitation? If it is attempted exploitation, then it's going to log failure and return 0. Exploitation death number 4. I think we're on death toll number 4. The last thing, the last kind of exploitation mitigation I want to talk about was something I kind of speculated about. Originally in Windows 7, the RTLP low frag heap alloc from context was wrapped in a try catch all. Basically, if anything happened bad, exception would be caught, it would return 0. If 0 was returned from that function, the backend would service the request, no questions asked. I kind of theorized that if you could do an overflow multiple times and attempt to, say, overwrite certain addresses or access certain pieces of memory that you were trying to guess, you could win, because if the memory address didn't exist, exception would be thrown, it would be caught, 0 return, you get a piece of memory. If it did exist, you overwrote it and you won. So that was a pretty easy fix. They just removed the try catch all, and that's not there anymore. All right, little summary for everyone, little rundown. You can see Windows Vista and Windows 7 have a lot of red X's. That is because they don't do things like have heap handle protection and non-determinism baked in to virtually allocated chunks and chunks in the low fragmentation heap. They're using dedicated bitmaps and counters instead of kind of just plugging them into data structures that already exist. They've added ways for programmers to immediately terminate a process upon linked list corruption, and added things like guard pages and avoiding arbitrary freeze. And lastly, even things that weren't, real in my mind, I just theorized that you could use this try-catch thing, a couple years ago, and it was removed as well. So this shows that Microsoft really took the time and effort to go through and look at what has been published and kind of react in a good way by fixing it, instead of yelling at me and Tarjei. That being said, I can't not talk about exploitation at all, right? So I'm going to go over a little exploitation tech. I don't think any of it's too earth-shattering. I'd like to say I have 1 1/3 exploitation techniques in this, and this consists of the third. I named it Bitmap Flipping 2.0. So what happens if chunks are in the low fragmentation heap? When they're freed, they need to update that bitmap, right? Because it keeps track of busy and free chunks. Well, since we're not relying on the data structure and free entry offset, how does it do that? It actually stores the offset within the index into the bitmap in the chunk header in the previous size field. And what you could do is overwrite this previous size field with a value that is greater than the size of the bitmap. It will gladly zero out a bit at that index within the bitmap. Since the bitmap is off the base of the heap user data header, you could potentially affect, say, C++ objects, other heap metadata, and so on. That being said, this thing's pretty moot for a lot of reasons, and I'll list a few. To free a chunk, you're going to need to get the UserBlocks, which is derived from the heap subsegment. The heap subsegment is derived by XOR encoding or XOR unencoding, depending on how you look at it, values which include that encoded chunk header introduced in Windows Vista and Windows 7 for all chunks. So if you have a sequential overflow and you munge that, this definitely isn't going to work for you. If you had an off by few or an overflow that started after the encoded header because the previous size is at offset 4, this may be able to do something. It may be an exploitation primitive, but I don't really have very high confidence level in this ever being useful. And this is just an example of what I said before. Let's say you have a bitmap with the size of 4. You overwrite a chunk to have a previous size of 20. When you free it at bit 20 from that bitmap, it's going to zero out a bit. You could potentially do something, inappropriate. On to the next one, the exploitation technique that I think can be viable. We talked before about how that heap user data header structure contained a first allocation offset, where to start the allocations, and BlockSize, which is a 2-byte integer that told you how big the chunks are, right? Well, if you could align two user block structures adjacent in memory and have a chunk that overflows from one into the other, you could actually come up with a scenario that looks much like this. You have 2 blocks aligned, and you overflow from one chunk into another heap user data header structure, and you can overwrite the first allocation offset and the BlockSize. What effectively this does for you is the chunk to be returned says, hey, once you get the index within that bitmap, take the address of the user block, multiply that index from the bitmap with the BlockSize, and add the first allocation offset. This has very similar effects to the free entry offset overwrite technique, right? Because you're going to be able to return a chunk that is outside the bounds of this container. That's going to be bad times. I mean, generally that's what I did when we wrote the ISFTP bug, is we got some stuff in memory somewhere and then overwrote a value and kind of prayed that that stuff would be there, and occasionally it was. So you could use this to the same effect. Again, there's some issues. Guard pages. If guard pages are enabled, this sequential overflow deal will fail because you're going to have an access violation. You have to position an overflowable chunk before a heap user data header structure. That's much more difficult than placing it before a free chunk, which was the prerequisite for the free entry offset technique. Tainting that bitmap that's used to determine where free chunks are could also end in access violations if overwritten with inappropriate values. Lastly, I think the chunk being returned from this calculation actually has to be free as well. It can't be busy. So there are quite a few prerequisites to get this working. But the nice thing is, once you overwrite it once, you can make allocations a bunch of time from that user block container, and it's always going to be tainted. So I think this is actually viable. Question, Mr. Cushman.
Have you gotten it to work?
I have gotten it to work on a program I wrote by myself. Do you have anything you want me to look at? All right, with that being said, it's Tarjei's time to talk about the kernel pool allocator.
Okay, so we've heard about the mitigations that were introduced in Windows 8, the Windows 8 heap, so we're now going to look at the kernel pool. Just to introduce the kernel pool briefly, it's more of a deterministic allocator, so you allocate from the beginning of a page and then subsequent chunks are allocated bottom up. It uses traditionally doubly linked free lists. These are ordered by block size. It's very focused on efficiency, meaning that it uses Lookaside lists, tries to use CPU cache, et cetera, and the kernel pool, if you're not familiar with it, is used by pretty much all third-party drivers and system components, the kernel itself, for dynamically allocating memory. So there's basically 2 pool types. There's the non-page pool, which is guaranteed to be present at all times. This can be accessed by any code regardless of the REQ level. You also have the page pool, which can be page out, for instance, to disk. And this can only be accessed below DPC and dispatch level. So there's basically these two basic pool types. And each of the pool that is defined is managed by what we refer to as a pool descriptor. And this descriptor is really the base structure that manages the lists of free pool chunks, the doubly linked lists. These lists are ordered by block size. So on x86, the block size is 8 bytes, while on 64-bit, the block size is 16 bytes. They're used for allocation up to 4,080 bytes on 32-bit and 4,064 bytes on 64-bit, I believe. The pool descriptor also keeps track of all the allocations and frees and pages in use, so it has like general statistics on the pool use. When you allocate a chunk, each of the chunks have a pooled header associated with it. So that header includes information such as the size of the chunk, the pool type, the associated pool descriptor, and the process pointer. And this is really what the allocator uses to do the merging and the allocation and freeing of the pool chunks themselves. So the pool header has really been the target of previous attacks on Windows, previous versions of Windows, such as Windows 7. So you have the definition of this structure right here. So the Windows 8 kernel pool is not fundamentally changing any of the algorithms, unlike what we've seen in user mode. It's more of a hardened version of Windows 7, so we don't have any significant structure changes, but we have a lot of more checks. So there's basically heaps of checks regarding the pool header, validating all the values properly, having validation on the linked list, so it's not only safe unlinking, it's also safe linking. They also use cookies to protect pointers of various kinds, and it also introduces what is known as the non-executable non-page pool. And this is to prevent an attacker from injecting shellcode into non-page memory, which complements another hardware mitigation called SMEP in a way. So the NX pool, as I said, is introduced in Windows 8, and it's basically a new pool type. So each driver has to request this type in order to get non-executable non-page memory. Most of the non-paged allocations in Windows now use this, and this also includes the NT objects. So if you allocate an object, you know that you can query its address through NT query information. Well, I forgot its name, but anyway, you can query its address, and then you can put shellcode in these objects, and you can chain them in order to create arbitrary length shellcode in kernel memory. With this, you can no longer do that. This also requires you to have dep enabled. So if dep is disabled, the NX pool is also disabled, and this is indicated by a pool flag. So when Windows uses this NX pool descriptor, it allocates two non-page descriptors per non-page pool, basically, and this is the executable and a non-executable. It also uses or has non-page NX Lookaside lists, and this is per processor. And it's per processor because of the optimizations of cache use, etc. And instead of using the pool type to differentiate between the two, it calls this MMS non-page pool NX function to determine whether memory should be returned to either the executable or the non-executable descriptor. And this function looks up the page table entry or the page directory entry and checks the NX bit in that structure. And this is, for instance, used by the free algorithm. So one of the major mitigations that were introduced was the kernel pool cookie. And this is used to protect, like I mentioned initially, various pointers referenced by the free algorithms and the allocation algorithms, such as in the Lookaside lists, or process object pointers that are needed to Whenever an allocation is quota charged, it is associated with a process, so it stores a process object pointer with the allocation itself. It's also used to protect certain cache line allocations, and we'll get back to how that is implemented. And the kernel pool cookie itself is initialized on boot in this function called initialize pool, and it's randomized with several system counters. So this is basically the function for seeding or generating this cookie value. So it takes the tick count, the number of system calls at a time, the interrupt time, the current system time, and calls this xgen random function, which returns a pseudo-random number, XORs all these values together, and then gives you the cookie. If the value is 0, it ensures that the value is non-zero by setting it to 1. So the cookie will never actually be 0 if you call this function. So there was this xgen random value, which is actually the function responsible for generating the pseudo-random value, which is seeding, also used in generating the cookie. And this is based on a lagged Fibonacci generator, and this generator is seeded by boot entropy in the loader parameter block, which is a data structure passed to the kernel by winload. And this is used by a number of functions now, like for image-based randomization, for PEB randomization, stack cookie generation, and a lot of other stuff. The boot entropy itself is gathered by winload, as I said, and it's from basically 6 different sources. So some of these sources will look at registry keys. They will query the pseudo random number generator if you have a TPM enabled. And if you have the new Ivy bridge, you will also use the new RDRAN instruction, which is a new pseudo random number generator embedded by the CPU. So in Windows 7, there was the research I did previously was a number of attacks in regards to how you could leverage kernel pool corruptions in exploiting vulnerabilities. And when you quota charge allocations, you typically store a pointer to the associated process object in that allocation. On 32-bit, you add the number of bytes by 4, so you store the pointer as the last 4 bytes, while in 64-bit, you put the pointer in the pool header itself. And when that allocation is freed, it checks this pointer. Not only does it check it, but it dereferences the pointer and finds this quota data structure in order to lower the quota. So this could be used, if you control this pointer, you could basically get an arbitrary decrement of arbitrary memory. So this is how this attack worked. You had the pool overflow. The first thing you overflow is the process pointer. So it was very easy to pull off. You didn't really need to, if you could control the length of the overflow, you didn't really need to corrupt any adjacent or bordering allocations. And this could be used to decrement any type of memory at any address. In Windows 8, they addressed this attack by XOR encoding the process pointer. So they use this pool cookie and XOR it with the address of the chunk that you're attacking or checking, and it also XORs it with the process pointer. And not only this, but it also ensures that when it has decoded this value, that it points into kernel address space. So in Windows, so when I demonstrated this in Windows 7, I could set up a data structure in user mode and create a fake process object, but now you would have to have that data structure in kernel mode as well, so it gets a lot harder, and you would have to defeat the decoding, which is considered infeasible in a way. So this is how this encoding works. So you have, you try to attack this process pointer, but now when the allocation is freed, it decodes and it checks if the decoded pointer is above system range start, and if it's not, it bug checks. If it is, it will try to do some additional stuff, but if you don't guess the right value, it will probably trigger an access violation or crash at some point. So Lookaside lists are used for servicing allocations quickly They do not require you to lock the pool descriptors, so it's very fast. It's singly linked. It uses like optimized instructions for linked list operations. And in Windows 7, you could, since it's singly linked, in Windows 7, you could simply overwrite the pointer to the next chunk on this list. And that would give you control of the next allocation, the address of the next allocation. So in Windows 8, each of these Lookaside entries are protected by a randomized cookie. And this is checked whenever you allocate something. So you try to corrupt this value, and you try to have the allocator return an address, like in kernel space, that you want to corrupt. Instead of giving you that allocation, whenever you free something, it will put this cookie, which is the pool cookie, XORed with the pool address, right in front of the pointer to, the free list, the Lookaside list pointer. On 64-bit, instead of storing it right before, it will store it in the pool header. So, even if you have an overflow, it's going to be from a previous chunk anyway. So it doesn't really matter as long as it's stored in the next chunk before the Lookaside list pointer. This protection is also used in the pending freeze list, which is an optimization by the kernel pool in order to avoid you to having to do pool descriptor locking every time you freeze something. They will have a long list of allocations or freed allocations that they will process in one go. I think the note about the release preview is that there's currently no cookie for protecting the pool page Lookaside lists. I've heard some rumors about this having been fixed now, so it just kills the last attack I had. Well, we have some more, so just wait for that. So this is the overflow, and you try to attack this next pointer on this list in order to get control of the next allocation. Now it checks, it has the encoded value, so it checks the cookie. So I briefly mentioned cache-aligned allocations. So when you allocate pool memory, you can request it to be aligned on a cache boundary, meaning that you won't have the double cache. You could potentially just have one cache miss, right, instead of two, depending on where the allocation, on which address the allocation is. And you do this by giving it the pool type of 4, which is a non-page pool cache aligned or page pool cache aligned, anything like that. And the allocator, in order to ensure that it always gets cache aligned memory, it will increase the size requested. So it rounds up to the nearest cache line size, and it adds the cache line size again. And the cache line size can be retrieved by looking at the nt-bang x cache line size value. And this greatly favors performance over space usage. So if you, on 32-bit, if you try to allocate 40 hex byte of cache line, of the cache line type, it will end up with a C0 hex allocation in order to ensure that the fragment that it needs is on a cache line boundary. And in carving out that fragment, it does not bother returning any unused bytes. It simply just lets the bytes be in that allocation. So since you have this unused memory, Windows 8 tries to insert a cookie whenever there's space available. Like if the allocator didn't serve you a cache-aligned allocation but had to scan forwards until it found the cache-aligned boundary, and having scanned forwards, it leaves space for this cookie. It tries to insert a cookie in this previous chunk. So this cookie is computed by XORing the used chunk, the address of the used chunk, with the pool cookie. And then it stores this cookie in that previous chunk. And for the allocator to know whether it needs to validate this cookie, it looks at the cache-aligned pool type. So the cache-aligned pool type is defined by this chunk that is on the cache-aligned binary in the pool header. And if this type is present, it notices it has to do the validation, while if it's not there, it doesn't care about, or it doesn't need to do validation. So this is basically how this works. So all of this is really the entire chunk that was initially returned by the allocator, or by the backend part of the allocator, and then it notices that this is not on the cache-line boundary, so it will scan forwards and set the pool header at this specific location, and then it notices that it has unused bytes, so it will insert a cookie in front of this allocation. So in Windows 7, Windows 7 was really the first operating system version that introduced any sort of mitigations to the kernel pool. So before Windows 7, you could exploit, or you could attack any sort of list entry structure used by the kernel pool and get a write for and get a win pretty easily. In Windows 7, they added safe unlinking, so it became a lot more difficult all of a sudden, and well, apart from these attacks, in that they validated each of these chunks and ensured that on W-linked lists, adjacent chunks pointed back to each other. The thing to note here was that the checks were generally made when a chunk was unlinked, and there were no checks when linking a chunk into a W-linked free list. So in Windows 8, they do both now safe linking and unlinking. So both when allocating chunks from a free list and when freeing chunks back to a free list. And this also includes, certain scenarios where you request a certain number of bytes but get more memory than you requested because there were, for instance, this free list was empty, so it had to pick the next one. And it even checks, when it puts that fragment back that it doesn't need into the free list again. It even checks that these lists are consistent. It also checks the entry, list entry structure for all the lists, not just the list entry structures associated with the pool allocations that it gets. So this kills one of the attacks on Windows 7 where they didn't properly check the F-link that pointed to the first allocation that was first entry on a free list. So this is basically you have this list entry structure of free lists pointing to entries on this list, and whenever you allocate something, you will have validation of all these values. So it's pretty good. So I think this is the last attack that was on Windows 7. So Windows 7 didn't check the pool index for a pool chunk. So the pool index basically defines what pool descriptor a pool chunk belongs to. And since it's an index, it looks up in an array of pointers which point to these pool descriptors. So what you could do on Windows 7 is you could simply reference an out-of-bounds value in this array, and that would dereference a null pointer. And since you were allowed to allocate a null page, you could completely control the pool descriptor, and you could control where all these chunks were inserted. So you could do a lot of stuff, including write to arbitrary memory. You could do a write for. It was pretty easy. So in this case, you can see on the left side the pool index. So it's like the second byte in the pool header. So you only needed like 2 byte overflow, and you could completely control all the free lists for which this allocation was free to. So in Windows 8, they do a very simple fix. They just check the pool index against the number of pools that are defined. So if we're talking about a page pool, they check the X number of page pool value. And not only this, but they also check that they also checks when the chunk is being linked into the list. So if you look at this, the way you could get arbitrary memory corruption in this case was that you controlled the F-link and the B-link values of the free lists in this null page pool descriptor. Since they check and when you link in, you can no longer do this. You can also not map the null page now because they have On 32-bit, VDM is disabled by default, so you need to actively go in and enable that subsystem. And on 64-bit, there's no VDM, so there's no need for, there's no way to map the null page. So in summary, they've done a lot of good things in Windows 8. In Windows 7, we had safe unlinking. Windows 8 improves this pretty dramatically. They also add safe linking. Pool cookies are used in mostly all of these lists now. We have pool index validation. We have encoding of the process pointers, which are associated with pool chunks. And we also have the NX non-page pool. So despite of all these fixes, there's a major drawback still, and in that the pool header is not encoded in any way. So you can still write into the pool header and possibly fake values as long as validation succeeds, right? And one other thing here is that it can be really hard to properly validate some of these fields. For instance, block size values. So because of the lack of dependencies in block size values, like the only way the allocator can determine whether a block size is of the actual size is by looking at surrounding chunks. And if those checks of looking at surrounding chunks are bypassed, then it could potentially extend like a limited corruption into an arbitrary in-byte corruption, so to speak. So there's two ways of doing this. It's what I call the BlockSize attack and the split fragment attack. So like I said, the block size and previous size are fields in the pool header that are used to determine the size of a chunk in a previous chunk. And this is used by the allocator, for instance, for putting it into the right free list, for doing merging of chunks in order to reduce fragmentation. And it's also used in validating these pool chunks. So when you free something, typically it will look at the block size of the chunk that you're freeing and use that to get the next chunk and check if that chunk's previous size corresponds to the block size of the chunk that you're freeing. The exception to this rule is when this next chunk is on the next page, because it doesn't validate across pages because the previous size will be null. There's no guarantee that the next page is even mapped in, so it doesn't have any checks on that. So for the block size attack, when you free something, it's put into a free list or Lookaside based on its block size. So if an attacker overwrites the block size, you can basically put this block into an arbitrary free list. And if you, moreover, set this block size to cover or fill the rest of the page, you completely avoid this block size previous side check when this allocation is freed. So this is kind of a simple illustration of how this attack works. You have an allocated chunk that you use in a vulnerability, a memory corruption vulnerability, and you overwrite, say you have like a 4-byte or 3-byte memory corruption, so you overwrite the block size of the next chunk, and you set that size to cover the rest of the page. Obviously, this requires you to know somewhat the locality of the chunk that you're attacking, but still, if you spray same sized allocations, you may be able to control this, but it relies somewhat on the circumstances around the vulnerability. So you set this chunk to cover the rest of the page, and then when that is freed, you can reallocate that memory like using a string, and you can completely control or partly control the memory of the allocation that you're attacking. So these are the basic steps here. You corrupt the block size, you free the corrupted pool chunk, make sure that it covers the rest of the page, and reallocate that free memory like using a Unicode string or something that makes that allocation. The next part is about split chunk pool allocations. So I think I mentioned this briefly, but when you allocate something, it will scan these free lists until it finds something of a suitable size. So it starts at the block size that you request, and if that list is empty, it will continue to the next block size, et cetera, et cetera. And when you get a chunk, it will notice that it's larger than the one you requested, so it will split the chunk and return the fragment back to the allocator. And it uses the block size to do the splitting. There's a good amount of sanity checking in this case. It checks all the F links and B links of all the lists. It even validates the pool index, so you cannot pull any pool index attacks. But there's no validation on the block size. So this basically enables an attacker to extend a semi-controlled 3-byte overflow into an arbitrary memory corruption by setting the block size to something larger than it actually is, and by fooling the allocator to thinking that, oh, I got an allocation here that is much larger than it actually needs. I'm going to free this part of the chunk that is not in use, that it thinks it's not in use, and back to the allocator. So this can basically enable you to free in-use memory. So in this case, you can have a corruption at the end of a page, which overflows into the next page, and you set this allocation being freed, and you set its block size to be double the value. And when you allocate this, it will notice that the block size is larger than it needs, so it will free this next piece of memory. And then you can reallocate that memory to completely control this next chunk on the page. So again, here are the steps. You corrupt a free chunk, you set it to something larger, and the allocator splits and returns that fragment back into the allocator or to the free lists, and then you reallocate that memory using, again, something predictable and controllable, like a Unicode string or something, like a Unicode string associated with an NT object, for instance. So they're not like groundbreaking attacks, but they still might be useful in some situations where you can extend something limited into something a bit more useful. So to wrap up and conclude, unlike the Windows 8 heap that Chris talked about, the kernel pool is really deterministic because it's biased towards efficiency. It needs to perform well. It uses Lookaside lists. It tries to use CPU cache as much as possible, avoid cache misses. And it allows an attacker to very accurately, make allocations from where it wants to, manipulate, do heap manipulation or that sort of stuff. And because it is, it's very likely that attacks on pool content will be a likely vector on Windows 8, even though the metadata associated with pool chunks are very hardened now. Pool content is still a very feasible way of attacking or leveraging pool corruption vulnerabilities. The block size attacks, like I mentioned, rely very much on pool determinism. So if you reduce it, you can really reduce the feasibility of these types of attacks. And it can also be addressed by improving the validation. So if you allocate something from a free list, and you make sure that the block size corresponds to the block size the list manages, you can kill off the split fragment attack. And additionally, the block size attacks also rely you to do very specific pool manipulation. So in some situations, like if you have a remote overflow, something like that, it can be impractical because you need to force these very specific allocations in order to pull off these attacks, basically.
Yeah, so you saw Tarjei go through his things as well, and I think it's pretty closely related to the user land. The Windows 7 exploitation tech is basically down the drain now. It's pretty well remediated, and it's going to be hard to use those techniques. In the user land side, determinism about the locality of chunks, whether in the low fragmentation heap or, say, virtually allocated memory, is not very useful or good anymore. I don't ever want to say heap metadata corruption attacks are dead, because as long as there's metadata there to corrupt, they will probably be used. But most likely you're going to try to attack some kind of C++ object or something else. But if you do have a very limited overflow where you don't control the contents, there's things like the heap user data header attack that could prove to be fruitful. Use after free bugs are going to be a bit harder, but not impossible. Microsoft fixed a lot of things. I think they paid a lot of attention and did a great job of fixing all the stuff up that was publicly available and people were using to write exploits with.
So all the attacks that were demonstrated on Windows 7 have been pretty much addressed in Windows 8. You have the proper safe linking, proper safe unlinking. You have the randomization of cookies or the randomized cookies to protect pointers. Still, the pool header is not protected. It's not encoded, so you can still overflow into chunks and totally, bypass checks. And because of this, there's no real need to repair the pool structures, et cetera, et cetera. Some Lookaside lists are still not protected. The pool page Lookaside list was not protected in the release preview, but I suspect it's protected now. But still, there's these other Lookaside lists that Windows uses for specific things that still are not protected. So.
One last thing. If you enjoyed any of this or want to get into it in farther detail, Tarjei and I worked pretty hard on releasing a paper that is going to be released with the slides as well, so you should check it out.
Yep.
Questions? Comments? Jeers? Cheers? Question? What's up? Uh-huh. So you won't know what's, you can't guarantee what's an adjacent memory, right? You can't say, I guarantee it's going to be allocated at slot 1, and I know in slot 2 there's this object I want to overwrite. Yeah, I mean, you can probably put it in a state where you're confident about the number of allocations and potential offsets that are there, but you'll never really 100% know anymore. Sweet. Thanks. Awesome.
Cheers.
Yeah. Let's go drink. Good job.